I'm glad to see you all are up and moving on a Saturday morning. I think you're going to have a lot of fun. I'm Marie Westfall with Oak Ridge Associated Universities. Welcome to our campus. This is the program that we're doing today, and for 5 more Saturdays, it's sponsored by Oak Ridge National Laboratory, and you will see a lot of scientists around. If you don't have to be the child of a scientist, there are lots of scientists here. One of the first things I want to do is to give you some safety information. If we need to evacuate for any reason, if you're near the front, you can go out this door or out this door. If you're near the back, you can go out this door and go out the doors you came in. There's some doors right there. If you're on this side, go out the back, and there's some other doors just kind of straight back down that glass hallway, and you go out that way. In any case, if there's an exit that's blocked, just go to the nearest alternative exit. If we need to shelter in place, which is what we call tornado drills for students, the bathrooms are safe places. And also you can go out this doorway right here, and there's a hallway right here that's also a safe place. According to weather, we should have none of those above problems. If you need a restroom, they're right out this door and just to your left, and there's also a water fountain at the restroom. When we get ready to do our final activity, we'll also have some popcorn for you guys. So don't get too you don't have to worry about really starving too much before you get home. It's my pleasure to introduce Dr. Ian Anderson. He is a neutron scientist, and I'll let him tell you a little bit about his background. But he is with Oak Ridge National Laboratory and kind of the kingpin of this operation. Welcome, Ian.
Wow. Thank you, Maria. I've been called many things in my life, but I think that's the first time I've been called a kingpin. You know. It's always the first time for everything, I always say. So, okay, who likes doing experiments? I'm trying to find the one that didn't raise their hand. You didn't raise your hand. You don't like doing experiments? So what we're doing today is a big experiment, right? As Marie said, this is the first of our Saturday Science, or Science Saturdays. I always get it the wrong way around, don't I? And so we're going to have some hands-on activities for you. The good news is you don't have to listen to me for the next hour and a half, right? That's the good news, right? And the other piece of good news is we've got some cool things for you to play with. Right? What I would like you to do at the end, besides eat popcorn, right, is give us some feedback if you can. Was it useful to you? What would you like to see different? Because as we go through this is, as Marie said, a learning curve for us, right? We've never done it before. So we would like you to tell us how it went, and whether it was useful to you, what you would like to see change, and maybe even some of the topics you'd like to see covered, right? Because we're going to go from hot to cool, right? So some of the experiments we'll be doing will be talking about high temperatures, right? The sun. We're going to, at the end, we're going to work out the theory of the rainbow. Has anybody wondered how a rainbow works? Right, so we're going to do that on the last day, right? Danny, who's sitting in the back, is going to have you play with ice. So we're going from hot to cold. But if there's anything else you want us to cover, let us know. Okay, so I wish I had Madonna here, but I forgot to download it, right? So we're going to talk about, at the end, and we're only going to get this at the end, the world's biggest microscope. Now, how big do you think the world's biggest microscope is? Oh, sorry, I should stop. Let me introduce the team, right? So I've been introduced. Matt, stand up. Matt is a physics teacher at Oak Ridge High School, and he put together all the hands-on cool stuff that you've got to play with, right? So thanks to Matt for coming in and doing that, right? Thanks. And as Marie said, there's a whole bunch of people. It takes a village to do this, as we realized last night as we were setting up all this stuff, right? So there's a whole bunch of people who've helped do this. Okay, so how big do you think a microscope is? I know it's 9:30. I've had some coffee. Oh, Joss, I said I was going to answer your question.
Wow.
Yeah.
It seems to me that to be a really good microscope, and considering the big, it probably requires an accelerator of some kind. Probably an electron accelerator. Use electrons.
It's close, right?
It could also use neutrons, because in there I saw someone saying that they can go through the stuff, which could also be useful.
Has he been to this course before?
If we're using an accelerator, then it's probably very, very big. Probably miles.
It's not, so he's not far off. It's not miles, but the accelerator you're going to see, and there's a very short version of it outside, right, is about 300 yards long, right? Plus a few bits on the end, right, Dale? Okay, so we're going to show you a really big microscope, but we have to get there through small stages. So first I'm going to tell you about materials, right? I have something here. Okay. You know that one of the biggest problems that's facing us, and I'm just going to take a little bit of time over this, is energy, right? And what I'm going to show you here is that solving the energy problem, you had to have energy to get here in the morning at 9:30. I've got mine, it's called coffee, right? So what I'm going to show you is the basis of a lot of our energy problems, or solving our energy problems. It's all about materials. Right? It's all about finding materials. Solar cells, right? We have to find solar cells. There's a lot of power, energy falling on the Earth. There's more energy falls on the Earth in 1 hour than the world needs in a whole year, right? So why don't we use it? Well, we don't have the materials that are really efficient at converting that energy into electricity. Storing alternative energy, right? You all want to drive an electric car, don't you? Right? What's the problem? Well, you've had your go, the guy over there. I'll ask you again, Josh, don't you worry.
Not enough places to be able to get energy to put in the car.
That's one thing, right? But going with that is, okay, if I have few places, I want the car to go further on one charge of the battery. Well, the batteries don't last very long, right? So you can't drive these electric. So we need to generate materials that we can make batteries that last for a long time. Here's another one, climate change, right? We need to use renewable energies. We need to do things like windmills. We need to store some of the materials that we make. It's all about materials here too. The electric grid, right? Josh.
The electric
I think Josh, you should come up here and work with me.
The electric grid we are using now has long mounted wire which are losing heat. We're
Right.
getting a whole lot of our electricity.
So what are we going to do about it?
Well, we could try to only have electricity flowing through the grid when we're using it.
So that's one thing. The other thing is we can make materials that don't lose power as we transmit the electricity, right? And those are superconductors, right? Okay. So I can tell you there's a number of people sitting at the back here who work on superconductors, right? They work on the physics of superconductors and trying to understand how we make better superconductors, right? Here's another one, nuclear fuel. Right? We want to close the nuclear fuel cycle, so when we burn these nuclear fuels, we want to be able to store them in a way or convert them to something that can be stored easily. It's again materials. In your homes, right, you pay for the electricity that heats and cools your home, right? So what you want to do is make that
more energy efficient.
More energy efficient, so yeah, it's okay, it's okay. I wish some of the others would get going as well. So we need to make materials that can either keep the heat out on a hot day or keep the heat in on a cold day, right? Good isolation materials. It's all about materials. Have you got it yet? What's this one? High mileage cars. It's back to batteries and lightweight materials, materials that don't weigh very much. So even if you do have a gasoline car, you can make it drive faster, further. Who knows what the ITER, who knows about fusion? Okay, tell me.
It's when you combine two light atoms, generally hydrogen, and it produces substantially more energy.
Right. So there's a big project in the south of France, right? It's called the ITER project, where they're trying to build a prototype fusion reactor, right? And the whole purpose of this reactor is just to prove that you can get more energy out than you put it in for a few seconds, right? And then they're going to shut it down and build a bigger one or a different one. You know why they're not going to run it for a long time? Because the temperatures. Josh, you know everything. I think you're going to give the next Saturday session. Go on.
Actually, the temperatures and the materials that are being collided can degrade the reactor and cause it to...
Right. The temperature at the center of that plasma, as we call it, is about 6 times the center of the temperature of the center of the sun. Do you know any materials that would stand that? So the not only wouldn't stand it, but so there's a lot of radiation coming from the center of this, right, and it also damages material. So we need to, if we really want to use fusion energy, we're going to have to find new materials that can stand these very high temperatures and these very high radiation flux, right? So there's more of this, right? New biofuels, I can't see that one myself, it's up there, carbon emissions, you know, if we do produce carbon, where are we going to store it afterwards? So it's all about materials, right? Have I persuaded you? So I come from Oak Ridge National Lab, a lot of these people sitting at the back there sleeping have also come from Oak Ridge National Lab, and a major part of what we do, not everything we do, is looking at materials, trying to understand the properties. So I've got a number of materials up there on the screen, right? Are they all the same? So, hey, I should learn, never ask a closed question that can be answered by yes or no, right? Okay, you got that bit right, okay.
They're the same because they all are made of atoms.
Okay, we're going to get there. That's the next step, you know, one bit at a time. So what's the difference in the materials? Anybody want to say? Yeah?
Some are solids, some are liquids, some are...
Sorry?
Some are solids, some are liquids, some are gases.
Right, some are exactly. Some of those are solid, some of them are liquid, some are gases, some are shiny, some you can see through. You know, they all have different properties, but they're all different.
I'd say they have different properties, like the car is able to have strength and integrity in the gears, while water might be able to cool stuff down quicker.
Right? So he's got a really good point. Because of the different properties of materials, we use them for different functions. And sometimes what we'd like to do is, if we can understand why they have those properties, right, we can then make a material, hopefully, right, and this is the kind of thing that we do, that does exactly the right function that we want it to do. Right? So for instance, you mentioned using liquids to cool. Well, some liquids cool better than others, right? So we might want to make a new liquid, right? Or we might want to make, for the car there, as we said before, we might want to make one that's really light so that the car can go further, right? But still keep the integrity and the strength that you talked about, right? So have I belabored this point? It's all about materials, right? Josh, I know you well.
If you make the car too light though, then it'll be able to stop extremely fast. I've not the human body designed to deepen to accelerate it that amount.
Yeah, so we don't make it light so it can stop so fast. He's okay. We don't necessarily make it so we can stop fast. We make it lighter so that we can take it further with the same energy. That's what we're trying to do. Yeah?
Although along that same vein, make the car lighter would make it more prone to the, if it was in an accident, to
break. So, yeah, I think I said, answered, I won't remember your names, so I'm not going to ask because I'm old, right? But you want to have the lighter material that has the same strength, right? So that shouldn't be an issue. It should, in fact, sometimes you make these materials that break slowly, so there isn't an accident. Actually, you absorb the energy of the collision, right? At the same time. So it's again about making materials specifically for a function. Now, why are those materials different? Why do they have different properties? Right, there's a good one. So some of them have different types of atoms in them, right? And when we put these together, we get different properties. Somebody who hasn't answered. You've answered. Yes?
The atomic composition, number of electrons, protons, neutrons.
Right, composition, right, of the atoms, right. So that's a good point. You see, you guys have got me to the next stage already. Okay, so here are three. So we all said that materials are made of atoms, right? And atoms are made of protons, neutrons, and electrons. And the guys in the back are going to tell you the only important part of that is the neutron, right? But we'll get to that slowly. So these are different structures of atoms, right? Guess what? Does anyone know what that is?
diamond.
Everybody agree? Do you agree?
No.
No, what do you think it is?
Pyramid.
Okay, he's right, so is he. Now, calm down. So, some people get too excited back here. So, yeah, okay, this is the diamond structure, right? And it does look like a pyramid, and we'll come back to that, right? Because that's important, right? It's really important. What's this? Yeah, Buckminster fullerene, which most of us, because we can't say that, say buckyball, right? So this is a buckyball, right?
Quite strong too.
Quite, you'll get there. What's this? Graphite. Right, tell me the difference. We'll forget the buckyball at the moment because, you know, I've only got 2 hands, right? So, leave him there for a moment. One of the exercises you're going to do next is to build these things, right? So we'll get to that. Matt's going to explain it to you in a minute. So, diamond, graphite. Tell me a little bit about the difference between them. Tell me something about, yeah.
They have different structures.
Yeah, they have different structures. Okay, good. What about their properties? Josh, we're going to let somebody else have a go. The lady sitting there, yeah. Different hardness. Which is harder? Diamond. This is really hard, right? Right? It's hard. Right? Okay, this is hard. Any other differences in the structure? Give somebody else a chance, Josh. I will ask you. You know, I'll come back to you every 5 minutes. How's that? Somebody remind me. Would I see? Yes. We'll get to that. She's made a very good point. They're both made from carbon, but that's where I'm going. But let's just go on with the properties. Good point. What's your name? Victoria. Okay. And I will forget Victoria. Okay.
Different bonds between atoms.
Yeah, that's another good point. There's different bonds between the atoms. Okay. What about the properties? Yeah?
The diamond is far more brittle than graphite.
It's more brittle. We said it was harder. What about some other properties? Yeah? Yeah, you. Hey, me.
Breaks off the layers.
Graphite, that's really important. Graphite breaks, we could say it's soft, right? So, does anybody want to, somebody come up here. Anybody want to do a test? Yes. Okay. I've forgotten about this. We're going to do a test. Now, I don't think we're going to be able to see this on the screen, so I'm sorry I made you set it up, but I think there's enough. Okay. Do you like diamonds? You are going to give it back afterwards, right?
Yeah.
Okay. There's a diamond. Show it to them. Hannah's got, it's not really a diamond, but it's very close, right? They wouldn't let me have one, right? Never mind. Okay, it's a diamond, right? That's a piece of glass, right? Can you try and scratch it and get it close to the microphone? Let's get it close to the microphone and we'll hear whether it scratches or not, okay? Can we do that? Is that okay? Okay, go on. Try and scratch that glass. Go on. Can you hear it? Can you hear it? Is that scratching it? Yeah, okay. So that's the diamond, right? That's really hard. Here's a pencil. We're going to imagine that's graphite, right? Now try scratching it. Anybody hear anything? Shh. Shh. Did it work? Can you scratch it?
No.
No. Okay. So, thank you, Hannah. So what did you find out about the difference there?
Diamonds are much stronger.
Can you help me put that back on there while you're at it? Good, that's good. Thank you, Hannah. Okay, so tell them.
Diamonds are much stronger than graphite.
Okay, good, Hannah. Thank you. So good, yes. Round of applause, Hannah. Okay. So there's your first test, right? And I'm keeping the pencil so I can point with it. So one thing, it's much softer, and as the gentleman at the back said that, one of them said that the differences between the bonds is much different. And so if you look at this, graphite is soft. It's sometimes used as a lubricant. Can you imagine that, right? And it's soft because the distance between these atoms is very large, and so they're not very strongly bonded, and these layers move across each other very easily, and that's why graphite is soft, right? There's no layer structure. You can't move one atom against another, okay? Very easily. That's why it's really tough and strong. One of the reasons. Just a minute, Josh. 5 minutes isn't up yet. There's somebody counting over here. So, there's another thing you haven't picked out yet. What is one other property, right? While you're at it. Think about it. Diamond, graphite, one other completely different property. Yeah?
Diamonds are much better at conducting heat.
Yeah, it's much better at conducting heat and electricity, yeah?
They both have different mass.
Well, the carbon atom has the same mass. Right, so it just depends how many you have. So effectively it's the same mass, but, well, different density. We'll go for that, okay.
Refractive properties, diamonds refract like quite well, whereas graphite.
Yeah, you've gone one step too far.
There's the obvious, there's obviously different colors.
Yeah, that got the obvious. So you went one step too far. Victoria nearly got it. One you can see through. The other you can't, right? I mean, graphite is like coal, right? You can't see through it, right? Diamond, it's transparent to light. You can see through it. And then you get to all the diffraction properties, okay? So they're very obviously different, right? But as somebody said, it's just the same. They're just made of carbon. There's nothing else in here but carbon, right? They're very obviously very different in their properties, but it's just the same stuff. So what's the only difference? You've all said it. Yeah, Victoria?
There's like the pressure in order to make the...
Well, that's how it's made. Just the very basic. You've all said it already. What's the difference?
The bonds.
The bonds and the structure, right? The only thing that's making these two things different is not which atoms are in there, but how they're put together, what structure they're put together in, and the bonding, right? That's all, right? So, what I want you to take away from this first part, because I think we're about to move on, right, very soon, is it's very important for us to know, work out where are the atoms inside the structure, because that's going to tell us a lot about the properties, right? Right, so that's what we're going to come to at the end of this lesson, right? This thing, right? This experiment. We're going to come to how do we look inside materials and see where the atoms are, because we've just worked out that's really important. We need to do that, right? So here's another set. I think we've got some stuff here. That's a diamond, right? You can see through it. It's beautiful. Girl's best friend. Wow, yeah, okay. I don't think they'll take this zirconia in. So here's some other structures that you make, right, from this carbon, right? You've seen the graphite and you've seen the diamond, right? Well, if we take a layer of graphite, we've got graphene, right? You've heard all about graphene, really important material. It's just a layer of graphite. Then you roll up those layers and you get carbon nanotubes and you roll them up into balls. You've got buckyballs, right? They're all just carbon, but they all have really different properties. So, I think it's your turn for a second, Matt. We're gonna now you've been sitting there getting bored with me, you're gonna go and do some build your own models. Okay, Matt.
All right, we're about to head to the room over to your right in just a moment, and we have 3 different activities that we're going to be doing, but before we do these, everyone needs to stand up, please. Raise your right hand, and repeat after me. I. Say your name. Yeah, very good. Do you hereby solemnly swear that I will not pocket the Cuban zirconia, shine lasers in people's eyes, or do other mischief with the resources. Alright, so you have all solemnly sworn that you will not be doing that today. Again, we want to be safe. The most important thing, though, is once we've built these models, we have to take them apart. So, otherwise, I've got 50 models that I'm going to have to break down piece by piece and put in boxes. Please don't fall into that fate. Close yourself up. Alright, and then head on up.
So it's not necessarily a fudge. So they have been thought of. That's what happened.
ready. So as I said, that was the warm-up. We're going to play with lasers next. Have you ever played with lasers? Okay, and we're going to do some cool stuff with lasers. Now, because we're a little bit, I've been talking too much, right? We're a little bit short of time, so we were going to split this into 2 parts. I'm going to run through to the end, right? And then you're going to get 2 activities out there. One, you're going to play with lasers, and you can come back and send your answers to me later, right? So we can give them my email, right? And I want the answers back, because you can do a real experiment this time, right? And I want the answers back, because I don't know the answers, right? That's one thing. Second, the popcorn bit, right? Don't get popcorn until you finish doing the hands-on exercises, because, you know, we're going to get greasy fingers all over all this stuff. And if you think this is a good idea, we're going to do it again, right? So there's some other people are going to come and use this stuff, so we'd like to keep the greasy fingers off it. So don't get the popcorn till you're really on your way out, right? Got it? No? Got it? Okay, good job. Okay, so let's move right along. You know, I get to this bit and I need 3 hands, right? So I might need some. Okay, so here's the question. We've done the exercise. We know that the structure is important, but how do we, and I'll try not to use that word, how do we look inside materials and see how the structure they're made of, right? That's the question, right? That's what we're going to do. So we're going to make a break, because I only have 2 hands. What's this? It's a laser, okay. Notice, for your experiments later, I'm not shining it at you. So when you do the experiments later, you're going to play with lasers, right? Don't, as Matt said, don't shine it in anybody's eyes. Make sure you're pointing at a wall. We do have goggles for you. But be very careful how you handle these things. You really can't do damage with them, but if you kept it in your eye for a long time, you'd probably have a blind spot. So don't do it, okay? So I'm going to play with this laser. Now, what is a laser? It's a beam of light. What is light?
A wave.
It's a wave. Okay, we're going to go into waves later, right? Just let me say for the moment, anybody know it's a wave, right? So light is a wave, and it has a wavelength, right? Right, the distance between 2 crests. And we'll come back to that. Anybody know what the wavelength is? Roughly, I don't care if it's right, roughly. It's, well, yes? Yeah, about 500 nanometers, and I'm going to change the units on you, right? So it's about 500 or 600 nanometers, right? You all know what a nanometer is, don't you? Good job. Okay, so I'm going to change the units on you because I can't think in nanometers. I'm old. I'm going to think in microns, right? So you can do that conversion, some of you. So it's about half a micron, right? Just remember that micron, right? A millionth of a meter. Is that right? Yes, thank you. A millionth of a meter, right, roughly. Half a micron. Now, anybody know what this is? You can't see from there, huh? It's a filter, a sieve of some sort, right. How is this filter, how is this made? Do you know how it's made? You know what it's made of? I should have had a picture there and I forgot to put it in. So this is made up of some wires, right? Some wires going in this direction and some wires going in this direction. So it's a 2-dimensional array of wires. Okay? Very simple.
It's not just 2-dimensional. Wires overlap like this.
Yeah. You are right, Josh. But for the rest of us, this is 2-dimensional, right? I agree it's got a dimension over there, but we're just going to look at the 2 dimensions, because I can't think in 3. You might, but I can't. Okay. So it's and you moved on me. Smart. 5-minute rule still applies, Josh. Wherever you're sitting. So, okay. So, 2-dimensional array of wires, right? And I happen to know on this one, because it's written on the side, that the distance between the wires here is 25 microns. Okay? Just keep that in mind. Now, what happens if I shine this light through this? The light will separate. Okay, let's give it a go. On a wall. Notice I'm not going to fire it at you. Here's the light. Shine it through there. This isn't very good. Can you see that? Okay, let's do something over here. You see that? The light separated and into a, it's better over there, isn't it? Into a series of spots, right? Okay. Now you could say to me, because I know some of you know the answer, but not everybody knows the answer, so I'm going to pretend we don't know the answer, right? Is you could say to me, okay, all you're doing is shining that light through the holes, right? And that's why I've got spots on the wall, right? So that's very boring, okay? Let me do another experiment. But
didn't you say the wavelength was half a micron?
yeah.
So the holes in the screen are bigger than the wavelength.
Yeah. But the beam itself is bigger than the distance between. Yeah, okay. So you're getting there, but don't cheat. Okay. So you might say that I had a very big beam there, that all I did was shine the light through the holes, and that's kind of boring, right? Okay, let's do something else. I've got another sieve here. Were you going to ask a question, Hannah? Yeah.
I know how it works.
Shh. Hannah, out. Okay. So here's another sieve, and because I can read, it says that the distance between the wires here is 150 microns. How many times bigger? 6. 6 times bigger. Right, so if all I was doing was shining the light through the holes, right, and they're 6 times further apart, you might expect, and you all know what the answer is here, right, that the light will, the spots on the screen are going to be 6 times further apart, right? That's what you might expect. So here's an experiment. This is something you're going to do, so get ready for it, right? Here it is. They're actually closer together, right? They're not further apart, they're closer together. So that's not what some of you would have expected. The rest of you have all done this at school, would have expected that. That is what we call diffraction, right? And that's an important concept for you, and it comes about because this is a wave, right? So let's look at waves. So if I shine it through here, right? If I shine it through a bigger sieve, the spots are closer together, right? So let's do one other thing, right? Now I know I can do that, if I could work out, sorry Marie, Marie's best scarf. Yes. Okay, so if I could work out what is the relation on this diffraction, what's happening here, right? And we'll come back to why it's happening in a minute. If I could work that out, right, what is the relation, then I could take any unknown material that's two-dimensional, Josh, array of fibers. This is almost the same, isn't it? It's just made of fibers this time, right? It's just made of fibers, right? If I could work out what the relation is between the distance between that mesh and the fibers and the spots, the distance of the spots on the wall, I could take any unknown material, shine it through, and work out what is the distance between the fibers, right? Do you think so? Think it's going to work? Okay, let's try it. Which bit do I have to shine through? It suits me, right? No? Okay. So here is a fiber. It's actually Marie's favorite scarf. Can you see that? It's probably, can you see? Same thing, right? And that comes because that's two-dimensional structure. Now, I could have, if Marie really needs to know, is this going to break easily? You know, she might need to know what is the distance between these fibers. Marie can go and do this experiment, right? We've already looked at what is the relation between the distance of the spots and the separation on the sieve. We can work out what that relation is, and that's what you're going to do afterwards. Left to you to do, right? Then I could take any unknown material, and I could say, okay, I can measure those spots. I can work out how far this is apart. Did you ever think of that before? No. Right, okay. So here's a great experiment. Now, and Marie wants her scarf back afterwards. Anyway, okay, so let's go back to this. So what we said was, you know, when we want to understand the structure of materials, we would like to do exactly that. I did it in 2 dimensions, right? We would like to know the distances between the atoms, right? Because if we can work out the distance between the atoms in 3 directions, three dimensions, Josh, we can work out the structure. Because the structure is just given by the distance between these atoms, right? We could do that. So here's the graphite again. Here's the graphite again, right? If you look at it like this, right, and I'll pass this round and you can do that. Please give it back at the end if you want. But if I look at it like that, I could have used this, right? But never mind, we're going to do this. If you look at these layers that we talked about before, and I look at it like that, that layer looks like a line, right? Right? So why can't I do this experiment now? Here I've got my lines, like in the sieve, right? And I shine my laser through it, right? I see where the spots are on the wall, and then I can work out the distance, as we did for Marie's scarf, and I can do that in every direction, and I can work out the structure, right? We got it. Winner. Do we agree? Who disagrees? Ooh, not even the guys at the back. Danny, you going to laugh again? Where is he? Okay, Danny's asleep. Okay. He's always asleep, by the way. Anyway, it's not. Okay, so what is the problem? So there are two problems we're going to go through. One is very simple, so I'll leave that one to the end. One is a little bit more subtle, right? So let's go. I'll tell you the simple one, and then we'll go through it in a minute, right? What the simple problem? There are two major problems. There are lots of problems, but two major problems with doing that experiment, right? One is, what is this material? Graphite. And what did we say about graphite? Yeah, what else did we say about it? Light won't go through it. Oh. Shucks. Right? I can't do the experiment, because if I can't get the light through the other side to see the spots on the wall, it's not going to work. One problem, okay? Here's another problem, right? And this is a little bit more subtle, but you've all got it. Let's see if it works. Okay. What's that? Okay, that's a wave, right? And that's, we said what light is a wave, right? And that's an example of a wave. I like that one. I'd like to be on the beach too. Okay. Have you ever thrown a stone into water? Water. Right? You get something like that, right? A ripple pattern. Okay. And you can see there's the wavelength between those two crests. That's what we call the wavelength in this case of this wave, right? Have you ever thrown two stones into the water nearby each other and watched what happened? What? So here you go. There's two stones. Right, well, I've already thrown them, right? Now watch. So here you can see these waves interfere with each other, and cause standing patterns here, right? We can do that again. Let's go back. I think it'll play again. All right? You can see that where they interfere, you get these standing patterns of crests and valleys, right? Okay? And as the stones go further apart, that pattern changes, right? So that pattern depends on the distance between those two stones. And I wanted to have a big bucket here and have people throwing stones in it and having a look at it, but they wouldn't let me. No, I really didn't ask. Okay, because you can show it quite well there. So we've got the idea. We've got a wavelength, and as these two things interfere with each other, they form a pattern here, right? Now that's exactly what happened with the sieve. Here's a wave, right? Here's a sieve, right? When the wave hit those wires, right, it disturbed it. Another little wave came out, and they interfered with each other and caused a pattern like that. And that's what causes the spots on the wall, right? That's diffraction, and it depends on the distance between them. So that's what we've done. We've done that, instead with stones and water, we've done it with light and sieves, okay? Now, so here's the subtle point, right? We've already said we can't do this experiment with the graphite because you can't shine the light through graphite. There's one more subtle point, right? Remember I said, and I was very deliberate about this, this is 0.5 micron, roughly. I can't do anything better than that, 0.5 micron. And the distance between the wires we've been looking at is a few microns or tens of microns. They're not a lot different, okay? Now look at this. Okay. Okay. That's a rock in a wave, right? We agree on that? Big rock. What is the rock doing to the wave?
Separating it.
Yeah, really messing it up, right? In fact, but it's separating it and it's causing little wavelets behind it. It's doing all sorts of things, right? If I had that same wave and I threw a little pebble into the water, would that wave notice it? No. So in order for the wave to be disturbed by an object, the object has to be a similar size. Right? So if I had a very small size, right, the wave isn't going to be disturbed at all. Right? And so that's another reason, it's a little bit more subtle, that the experiment doesn't work with light and atoms. Because, right? Let's have another picture here. So remember that. The object has to be a similar size, right? Similar, you know, it doesn't have to be identical, but not millions of times different. So what can you tell me about the distance between atoms and the wavelength of light? We want to measure the distance between atoms. What's the difference? Sorry? Yeah, they're bonded, but what about the size thing? We're talking about size, right? And I won't go there, right? So we're talking about the distance, yeah?
Size between atoms is incredibly small.
Right.
There's almost no space to put a light on.
But it's not a space thing. Remember, we're talking about the size of the object has to be similar to the wavelength, right? So here, look at this. And if you can understand this, you know, some of you will understand it and so on. Here is some objects, right? These are natural objects and these are man-made objects as on a distance scale. So I've used meters, right, because that's where I come from. You should be able to use meters, but if you don't, yards will do. They're almost the same, right? And so going down from, you know, just a centimeter down to very small distances. Now, this is the kind of distance we're talking about, the distance between atoms, nanometers, right? The wavelength of light is up here, right? There's 1,000 times different, right, between the wavelength of light and the distance. And I said they have to be similar. 1,000 is too much, right? So the experiment doesn't work because the wavelength is too big compared to the distance between the atoms, right? And it also doesn't work because we can't shine through it. So what we want to do is to find, so we know that the idea works, right, but we know it doesn't work with light. So we need to find some wave, some probe like light, that has the right wavelength, right? And then we can do the experiment. So what would you suggest? You all go to the doctors, so what would you suggest? If you say neutrons, I'll shoot you.
X-rays.
Good job. I didn't, okay, yes, okay. So we want something in there, right? Okay. I don't know that. I think it's Mike Simonson, but never mind. No, it's not. So that's a person, right? And we can't shine light through a person. We've tried, right? It doesn't work. And as the young lady said, we can shine X-rays through. Okay? So maybe, and X-rays do have the right wavelength, so think about that. So maybe we can use X-rays. And we can. So there's a lot of experiments we can do just this experiment with X-rays. But, what's that? So it's an engine. Can you shine X-rays through an engine? Let's give it a go. That was easy, wasn't it, right? Right? You can't shine X-rays through that, they won't go through. So I want to do experiments so I can see inside materials and see how they're made, and I can't get the X-rays in. The X-rays won't go more than a few microns into that. Right? If I have a very small piece, I can do it, right? But if I have a big piece like that, I can't. Look at that. Did we go through that? Those are neutrons. That's radiography done with neutron beams shining through an engine. And you can see those neutrons went straight through. Right? Went straight through, and we can shine through the material. So, here's the thing, right? Not only, and you have to take my word for this, right? But you can come and do some experiments and try. I shouldn't say that. Okay. Not only do neutrons go through materials, but they have a wavelength. Neutrons are also waves, like light and X-rays, right? And they have a wavelength just the same as the distance between atoms, right? And so I can do these experiments. So here you go. So this is what we want to do. We've got it, right? This is a special neutron laser. Here you can see this is the SNS Neutron Laser. It doesn't quite look like that, right? It's close, right? So we've got our SNS Neutron Laser, right? We shine it through materials, right? And we look at where they go afterwards, and we can work out the structure of materials. It's as simple as that. So it's really cool, right? We can look inside things as big as an engine, look at the atomic distances, and work out exactly how that structure is made. So do you think that's cool?
Yes.
Yes.
Good. Okay. Where are we going to get the neutrons from? We're way over time. Is it okay? Nobody wants to go home yet, do they?
No.
Yeah. Yes? Radioactive materials? Few. You won't get many. Slamming atoms into each other. Right. He's been there before. Okay. So that video is not going to work, but never mind. This is one way to do it. We'll get this cleaned up and get videos next time we work. Okay. What's that? It's the nucleus of an atom. Yeah, right. And what's inside it? Right, the protons are red, always, and the neutrons are blue, always. Right, it's not because they're sad, they're just blue. Okay, so if I get a nucleus that's got lots of neutrons in it, and there are many of the heavy metals, you know, the big atoms, have lots of neutrons in them. So what we can do is come in with something and knock them out. That's one way of doing it. Nuclear reactors, we're not going to talk about nuclear reactors today. So I can knock them out. So this is a proton. If I hit these nuclei fast enough with enough energy, I can knock them off. It's like hitting a rock with a hammer. Have you ever tried to do that? We didn't get that either. We could have done all this, right? Wow. Okay. Get a hammer, hit a rock. What happens? Bits come off. Well, the same happens in the atomic world. We hit that nucleus with a proton, bits will come off, and neutrons will come off, right? Just turns out that these have to be very high energy, right? Very high energy to knock off these neutrons. And then we collect these neutrons and we fire them at materials. We watch where they go with special things called detectors. And we can do experiments. Now, where do you think in the world we can do that? A particle accelerator. Okay, where do they have particle accelerators? Oak Ridge National Lab. Anybody got the shirts on? Come on. Yes, SNS. Go for it. Okay, so we'll be quick. This is Oak Ridge National Lab, right? This is where I work. Let's get one of these, right? And right at Oak Ridge National Lab, you have the Spallation Neutron Source. I can't say it like a lot of people say it around. Well, how do you say it? Anyway. So, spallation, that comes from just that process I talked about. Hit something with a hammer, you spall off bits. So the Spallation and Spallation Neutron Source says we spall off neutrons by hitting them. Hitting an atom very hard. So this is it, that's what it looks like, and it's a pretty big microscope, right? That's a microscope. That's all we're doing, we look inside materials, right? It's a microscope. That's how it works, and outside there's a simulator that Dale and Mark and Renee and Charlie spent 3 hours putting together last night. Actually, they're pretty good, because to build SNS took 7 years. So they put one up in 3 hours. Good job. Okay. So you're going to run through and try it. So basically, I'm going to go very quickly through this because we're running out of time, but we can do it another time if you want. It's an accelerator, right? So the target is here. That's where we actually have a target of mercury. Mercury is a liquid, but it's also a very heavy metal. So mercury has lots of neutrons in it. Yes. Right? So what we do, we have this very long accelerator, and what that does, it takes protons, accelerates them up to 90% of the speed of light. That's pretty fast, huh? Right? We wrap them a few times around there for certain reasons. We can go through that if anybody wants to ask me. We wrap it, and then we fire it at this target, and we knock off neutrons. Lots of them. Every proton produces 25 neutrons, right? And then we take those beams of neutrons out to these experimental areas here, and we shine them through materials, and we look where they go, we work out the structure of materials. It's as easy as that. It's pretty simple, right? Okay, so as I said, we accelerate protons, we wrap them a few times around, then we fire them to the top. How many times a day do you think we can do that? Once. Any other goes on this? Twice. That's a big step. Imagine that we do that 60 times a second. Danny, did you wake up? Okay. 60 times a second, we accelerate this proton beam, we wrap it up, and we fire it at target. So 60 times a second, we have very intense beams of neutrons that come out through these experiments where we do experiments. That's cool. Right? Okay, so let's, I think the next one is a video. Let's see if it works. Okay. Shh. Ooh. Yeah, I'm going to go back. Sorry, I was trying to turn up the volume for you there, and I don't know my new computer very well. So let's look in detail how SNS works. Let's go right to the beginning, or front end, where in a hot plasma we produce mini pulses of hydrogen ions. That's just protons with 2 electrons attached. Each mini pulse contains roughly 150 billion protons. We accelerate about 1,000 of these mini bunches of protons in sequence in a 300-meter long linear accelerator, up to 90% of the speed of light. In scientific terms, that's 1 gigavolt of energy. At this speed, you could do 35 round trips between New York and Los Angeles in 1 second. We do this acceleration using alternating radio frequency electric fields that have to be timed to each other and controlled within 100,000th of a millionth of a second. Along the path, we also have to keep the beam focused with magnets whose fields are 10,000 times stronger than the Earth's magnetic field. Now, if you were to stand at the end of the linear accelerator and watch the 1,000 mini pulses go by, they would take only 1 millisecond to pass by. That's about 400 times faster than the blink of an eye. And it would look like a string of protons 250 kilometers long. That's 155 miles long. That's very long, right? So then we take the string of protons, that's now 150 trillion protons, and coil it 1,000 times around an accumulator ring, which has a circumference of 250 meters. By doing so, we have compressed the proton string to about 250 meters long and less than 1 microsecond. That's 1 millionth of a second. When the accumulation is finished, we turn on some very high-powered magnets to kick the string of protons out of the ring and fire the very high-intensity proton pulse at a target. The pulse of protons that hits the target contains about 150 trillion protons, is 700 nanoseconds long, and has an energy equivalent to a 16-pound bowling ball traveling at 100 miles an hour. That's enough energy to knock your socks off. This whole process, acceleration, accumulation, and fire at the target, only takes 1 millisecond to do. That's 1,000th of a second, and we do it at 60 times a second. So effectively, we're firing 60 of these 16-pound bowling balls at the target every second. So it must be a very special target. The target is a container full of flowing mercury, actually about 20 tons of mercury. That's a lot of thermometers. Though, since mercury is very dense, the total volume of mercury is only about 1 cubic meter. So why do we use mercury? Well, mercury is a heavy atom with a neutron-rich nucleus. Each nucleus contains 121 neutrons and 80 protons. The high-energy protons in the incoming beam from the accelerator knock off, or spall off, neutrons from the mercury nucleus. In fact, each proton produces about 25 neutrons. So let's do the maths. 150 trillion protons per pulse times 25 neutrons per proton times 60 pulses per second. That's more than 200 quadrillion neutrons per second. Now, unfortunately, these neutrons have very high speeds, or short wavelengths, so we have to slow them down in moderators made of water or liquid hydrogen at just 20 degrees above absolute zero. And now we're ready. We send these intense pulses of slow neutrons along beam guides to the instruments, where we have the sample ready that we want to study. We have many instruments running at the same time. The beam guides that take the beams of neutrons to the instruments are very special too. They are made up of mirrors that reflect neutrons very effectively and keep them focused as they travel towards the sample. When the neutron beam hits the sample, it scatters or diffracts as we saw earlier. The problem is, of course, that we can't see the neutrons, but we can detect them in big detector arrays which tell us where the neutrons went, i.e. where the spots are on the detector. We connect these big detectors to fast computers, and by measuring where the neutrons hit the detectors, the computers can calculate where the atoms are in the sample. Of course, we have all sorts of programs that help us visualize the structures we have measured, but in principle, it's all just as easy as that. And now you are experts. Okay, I'm sorry about the sound, didn't work very well, but we can give the whole, we can make it available on the web, so you can go and listen by yourselves if you want. So that's what SNS does, and you can see it's just a very big microscope for looking inside materials. Now you're going to get some chance to do this. There's some pictures of what it really looks like. Right, here's part of the accelerator, this is another part of the accelerator, but you're going to try it outside. It takes a lot of power. That tunnel there is 300 yards long, right? To get the protons up to very high energy. This is where the targets are, and when we have to change those targets, you can imagine they're very radioactive. They only last a few months, so we have to change them with robots like this. So there's all sorts of technology inside this machine, right? As I said, it took 7 years to build it, right? And how much do you think it cost?
Too much.
Too much. A lot is probably a good. $1.4 billion. Okay. Here's some more pictures of it. These are what the instruments look like here, where the neutrons come, and this is where we're putting this sample we want to look at, and then we look at them where these are not really detectors, but the detectors are over here. So you got an idea, and you can, I think, get tours during your lifetime of this facility. So this facility was judged by Popular Science as being the third most coolest big science facility in the world, right? Now, I think they got it wrong, it's the best. But anyway, so these are some of the areas we're looking at. I'm not going to go into that, right, because there's lots of things. When I say materials, you'll think I might be talking about engines all the time. I could be talking about drugs, right? We can look at the structure of drugs and we can help make new drugs. We can look at chemicals. We can look at engines. We can look at almost anything. Anything that has atoms, almost, we can look at. So that's where you need to go, right? Now I think, oh yeah, okay. So before we go on, so that's the end of the show. Lots of questions. Before Matt comes on, tell you what you're going to do now. Right now, you get to do it yourselves, right? So we've got lasers and we've got sieves, and I want to know. What I'm going to want to know, back by email, is what is the size of those sieves, right? What is the distance between the wires? You work it out, right? You're experimentalists now. You're experts. So Marie asked me for some reason to tell you where I came from. How I got here, right? Well, I got here because she called me one day and said, well, no. So, very briefly, as Hannah said, right, I don't come from East Tennessee. Did you get that? Somehow, okay. So I come from England, right? I was born in England, I went to university in England, and when I was doing my graduate studies, it was down in the 70s when we had the first energy crisis, right? And one of the areas that was being studied very carefully was looking how you can store hydrogen inside materials as a storage mechanism, right? So I started looking at how do you store hydrogen in metals, right? And the metals actually can store a lot of hydrogen. And I use neutrons. Right, so I use neutrons to look inside those materials and see where the hydrogen was and how it was moving, right, so that we could generate new hydrogen storage materials. And then I got into more the technical side of it and thinking, well, producing these neutrons, we need lots of neutrons to do these experiments. How do we make the machines that produce these neutrons, and how do we guide them and how we detect them? So I got into the side of actually the neutron side rather than the research side, and I did this in France. So I worked in France for 6 years, and then I came to America for a couple of years, and they sent me back. Right? So I worked in Washington, D.C., where they have a nuclear reactor, doing the same kind of things for a couple of years. And then I went back to Switzerland, where they were building one of these kind of facilities. And so for 5 or 6 years, I worked in Switzerland, right, doing this, and then spent yeah, I moved around. And then for a year in Spain. So, you know, science is fun. You can travel, right? Right? And then I came back to Spain. No, I went back to France for 10 years to build some of these. And when you, here's a point. I don't want to belabor this, but some of the technology that I was working on was cool enough that it's used for making chips, right? Electronic chips. So I actually helped set up a company to make chips, right? So this, see the diversity here? And then I came here. That was 10 years ago, and I'm still here. So Marie asked me to tell you a little bit how I got here, so that's how it is. So, Matt, I'm around for questions. It's your turn.
You're going to hang around for questions here?
I'll be around mingling, because you need to...
Right. Yeah. Okay, so here's what we're going to do. If you've been looking at your watch, shame on you. But if you have been looking at your watch, you realize that we're just a little bit over. In fact, there's a clock in the back. You really want to see how over we are. But we want to do science, right? And smartly, we saved the lasers for last. So in the room over here, that you were just working in, and on those tables on the back, for those of you working there, we are now going to do the same kind of laser demonstration that he did here, with the different colors of lasers. You'll get those lasers from your Sciences volunteers. One of the things that you do need to know is that we want to be safe with these lasers. No lasers in people's eyes, please, or any other body parts. We want to shine these lasers to the walls in whatever room we're in. And let's try not to shine it across to the wall that's got people in between it, as best we can. Also, we have the coolest goggles known to man and woman.
Oh, yeah.
Yes.
You know, it matches, right?
It matches. That was on purpose. You definitely want to be wearing these. I will warn you, though, if you're going to be marking dots on a piece of paper that are red, and you've got a red filter, you're not going to be able to see it. So you may have to peek up like that at what's on the wall to get that measurement. But there's graph paper, there's meter sticks, the calculation, the formula for how you would calculate that distance between the wires and the mesh has been given to the Sciences volunteers, and they can help you work that out if you're getting stuck. Also, when you're finished with playing with the lasers, you can go through the simulator. Strongly recommend you go through the simulator. On your way out the door today, there's popcorn and water. Just a little snack before you get off to lunch. So take advantage of those things as well. Anything else I missed?
So my suggestion for you is to get the laser to somebody